And it doesn't have a central unifying theme like the first talk. The first talk was really about something. And this one is going to be, well, it's just a jumble of a bunch of identities that I think are interesting and maybe informative. But I couldn't really discover a unifying theme, except that I think they're interesting. So I'll start by stating a multivariate version of the Lagrange implicit function theorem. There are several different equivalent versions that put the formula in kind of superficially quite different forms, each of which is useful in particular ways. But I'll just state one form. And the McMahon-Master theorem, which predates it but is an important special case of it, then the Cartier-Fuada theory from the late 60s on partial commutation monoids. I'm going to explain that with a minimum of technology. It's a really interesting combinatorial inversion formula, and it has something to do with McMahon-Master theorem as well. Carlin, McGregor, Lindstrom, Gessel-Viano. I don't know if there's a shorter name for what this is. It's a determinantal formula which is quite important in the theory of symmetric functions. And it has a really pleasant proof, which I won't tell you about. The transition from 3 to 4 is that the proof technique is similar in both cases. You construct a sign reversing involution that cancels almost everything in sight, and you're left with a predictable leftovers. So number 4 is a determinant formula. Number 5 is a determinant formula. So locally, everything has something to do with the next thing, but there's no global something to do with everything. So Kirchhoff's matrix tree theorem, of course, is classical because Kirchhoff did it 161 years ago. I think it's really one of the first solid results in enumerative graph theory. And there's something extremely recent that generalizes Kirchhoff's theorem due to people in the audience. I don't want to steal your thunder, but I think that's one of the nicest things that I've seen in recent years. So I want to talk about a little bit about that. Okay. So multivariate Lagrange. Instead of having one indeterminate, we've got n. They commute pairwise. And I'm going to have two different sets of indeterminates just so I can keep my generic generating functions in the u's separate from my solutions in the x variables. So the input is a commutative ring K and n plus 1 power series with the way I'm stating it here, I think it doesn't, but you probably run into problems if it doesn't. Yeah. I can't think of a good reason why it doesn't why it shouldn't. Yeah. But there are no denominators in the formula I'm going to show you. It's just that you might end up with the right-hand side being 0, and it gives you no information. So the first part of the statement is the same as the univariate case, but now you've got this system of n coupled functional equations, and they have kind of the form that you would expect upon generalization from the univariate case. The jth solution is x sub j times g sub j of all of the solutions together. So they're kind of coupled, but the recursion that tells you the jth solution is multiplied only by x sub j. And so they're coupled in kind of predictably separable way. And here's the formula. It's a bit of a beast. So, of course, this is now a power series in n different indeterminates. So you look at a typical monomial, x1 to the alpha 1, x2 to the alpha 2, or alpha 1, alpha 2, and so on, are natural numbers. And again, I'm going to ask for what the coefficient of x to the alpha is in an arbitrary power series evaluated at these solutions, R1 up to Rn. And the right-hand side gives you a formula for that in terms of only the input data. You take the corresponding monomial in the u's in this power series. F of u, now this is g of u to the power alpha. Remember, this is g1 to the alpha 1, g2 to the alpha 2, and so on. And then you've got this determinant of a matrix. So where does this come from? This is the Jacobian of some system. I don't know. It's not an easy proof.
So even in the case n equals 1, this is an alternate version of the Lagrange inversion formula that avoids the 1 over n, and therefore that's why it avoids the condition that k has to contain the rationals.
Yes, I guess so. The thing is that that was the point I wanted to make. If you specialize this formula to the case 1 over n, to the case n equals 1, the left-hand side is just what we had yesterday. The right-hand side is something different. And in order to change this right-hand side into the right-hand side we had yesterday, you have to introduce a denominator. But this doesn't have the denominator in it. Yeah.
Right, I think it's equivalent to the other one by some kind of integration by parts.
Yes, that's exactly right.
So in some sense, this one is a little bit more general because you could work in a ring that doesn't contain the rationals.
Right. Yes. Okay, so I'm not going to say anything about the proof of this, but it's similar magic with formal power series. A special case of multivariate Lagrange that predates it, as I mentioned, is the McMahon-Master theorem. It's a special case when the power series governing the recursions are just homogeneous polynomials of degree 1. So linear forms in the u variables. And I won't go through the derivation. It's not actually all that easy from the form of multivariate Lagrange that I gave you. But this is the statement of the McMahon-Master theorem. You've got to do some substantial monkeying around. So, well, if I had more time, I would give you some illustrations of how this can be used to prove polynomial identities that are quite opaque to see. I mean, there are kind of classical identities in Q series that come out of this rather mechanically, and I think that's why McMahon called it the master theorem. But I found something in a recent paper of Garofolitis, Lee, and Zeilberger, which is a sort of physical interpretation of this formula. At least they attach some words from physics to it, but I don't know what it means. And I mean, any of you who understand physics, please tell me what this means physically. So just a simple bit of algebra takes this statement of the identity and see, so both sides are elements of the underlying commutative ring K. If I, let's see, if I just sum over all alpha, then I'm not going to have any x variables appearing on this side. So that's what I'm doing here. And you just don't have any x variables here. And if you think about the way the the subscripts are attached here. If I want to get x to the alpha from here, I've got to take x sub I, alpha I times. I'm going to have to take alpha I terms that have a c with an I in the first index. So you can recover the alpha from just, you don't need the x's there. You get this statement here. Now, if you think of the matrix C that comes into play in this formula as representing a linear transformation from a vector space V to itself, so an endomorphism of a vector space V, then there are induced endomorphisms on matrices, on vector spaces constructed from V. So you can take the symmetric powers of this vector space V, and there's an induced endomorphism on the symmetric powers on the mth symmetric power, and similarly, there's a induced endomorphism on the mth exterior power. And some rather mysterious formulas for me is that this left-hand side is the trace of the mth exterior power. And the denominator of the right-hand side is this generating function for traces of the exterior powers. And so you get this identity for traces of these induced endomorphisms, which is called the boson-fermion correspondence, and I don't know why. I can see some skew symmetric stuff over here and some symmetric stuff over there, so I know which side is fermion and which side is boson. But what does this mean?
But in physics, a boson-Fock space is just another name for the symmetric tensor product, and
yes.
fermion is the exterior product.
I wasn't quite confident enough to say Fock space in public, because I don't, but I was pretty sure that that's what those were. Yeah. So
this is true. I don't know.
This is equivalent to the McMahon-Master theorem. It's called the boson-fermion correspondence. But what does it mean physically?
There is something called bosonization, where you can somehow replace fermions by bosons.
That's a two-dimensional thing.
Huh.
This is just an algebraic relation.
Just an algebraic relation. Yeah, but okay. So I would be interested to know what this means physically.
What is T here?
T is just an indeterminate. I'm sorry. Yeah, it's just something to keep the degree of the symmetric powers separate. And T
is a matrix?
No. T is just an indeterminate. It's a symbol.
Oh, it's just one number.
I didn't want to use the lowercase t because that got me confused with the trace.
Oh.
Yeah.
Can you run back one slide?
Of course. So yeah. So I kind of understand this formula. I don't quite understand this one. Why the trace of the symmetric power should be the left-hand side of the McMahon-Master theorem. I don't know. But it's kind of neat. Okay.
So somehow it is related to the fact that you don't normalize these Lagrange polynomials, right? Because your data is 1 on all the Lagrange polynomials. So you need to recover the constant function, but you don't recover the constant function because you didn't normalize correctly, and that's your normalization.
Oh, okay.
Sorry, Dave, what do you find unnatural about the first formula?
No, there's nothing unnatural about it. I just don't know. I just don't understand why it's true.
Do Zeilberger et al. Use Clifford algebras at any point here?
No, they just state this without proof.
This boson-fermion correspondence, do they refer to some physicists who previously had the same formula?
I don't know. I didn't check the references, but you should probably ask Garofolitis about that.
This is just geometric series.
Yeah. So it's a geometric series in the positive degree in terms of this.
Sum t to the m is 1 over 1 minus t.
Yeah. Well, I want to give you another instance of this pattern that I do understand.
Maybe it's like complete symmetric functions versus elementary ones.
You're good. It's exactly like the complete symmetric functions and the elementary symmetric functions. Just like you said. It's the exact same formal relationship between the generating functions. So you've got a countable set of indeterminates, and the elementary symmetric functions are basically the kth elementary symmetric function is the sum of all k subsets of indices. So strictly increasing sequences of indices x sub I1 up to x sub ik. And the complete symmetric functions is the same with weakly increasing sequences. These are symmetric functions in the sense that any permutation of the variables leaves these functions invariant. So if you look at the generating functions for these guys, the generating function for the elementary symmetric functions is given by this. And it's easy to see because for each of these factors, you can either choose the term 1 or you can choose the other term. And you have to do that in such a way that you get a finite power of t. So you'll end up choosing t to the k for some k, and then you'll end up choosing some k subset of indices I. And you'll do that in all possible ways. So the coefficient of t to the k is the generating function for all k subsets of the variables. And completely analogously, if you use geometric series here instead, then you can take x sub I as many times as you want. And that corresponds to the complete symmetric functions. And from the right-hand sides of these equations, it's obvious that you have the same functional relationship between the generating functions as in the boson fermion correspondence. So elementary symmetric functions are something about fermions, complete symmetric functions something about bosons. Okay. So this is actually the very simplest special case of a more general situation in which this relationship appears, called the Cartier-Fawada theory, or heap inversion. So the setup for
your previous boson fermion correspondence, the McMahon thing.
yes.
Yes. Can't you get that now from this corresponding thing with symmetric functions? And if you suppose that the C's here are real or complex numbers, and then you make an eigenvalue, look at eigenvalues of the matrix C and obtain it, I think, from the other result.
I think you're right. Yes. I mean, that's generally the way it goes. Is that this kind of thing is interpretable from symmetric functions of the eigenvalues of the matrix.
Yes.
And so, yeah, right. It's easy. Okay, so there's a more general situation in which this functional relation holds. So you start with a simple graph, and I'm going to look at stable sets of vertices, sometimes called independent sets, but I like to reserve the word independent for an entirely different concept. So a set of vertices is stable if there's no edge with both ends in that set S. So the subgraph that it induces is a graph with no edges. I'm going to have an indeterminate for every vertex, and I'm going to look at the generating function for stable sets in my graph. So I just sum over all subsets of the vertices that are stable sets, x to the power s, where this is a shorthand for product over the vertices in S of the corresponding indeterminates. Correct me if I'm wrong, but in physics, this is a zero temperature partition function of a lattice gas with repulsive nearest neighbor interactions. Stable set enumerator is shorter, but it doesn't carry the same connotations. So they're the same.
Depends on what is your graph. It will be my cluster expansion after.
Oh, yes, that's right, on the cluster graph, right. Yeah. Yeah. Okay, so this stable set enumerator is going to be on one side of this boson-fermion correspondence, and on the other side there's a different combinatorial object. What I'm going to do is I'm going to say that these variables are only partially commutative. Namely, you've got the graph structure, and so for any pair of vertices, you know whether those vertices are adjacent or non-adjacent. And I'll say that non-adjacent vertices commute with one another, but adjacent vertices are incompatible. They don't commute. So you can't swap the order of adjacent vertices. They interfere with each other somehow. And then you look at V star is the set of all finite sequences of vertices, or the indeterminates that correspond to them. And so that's the fully non-commutative version of monomials. And you mod out by the equivalence relation generated by these and only these commutation relations. So this is a partially commutative version of monomials. And the Cartier-Fuada have this beautiful formula. The reciprocal of the stable set enumerator, where each variable is replaced by its negative, is exactly the generating function for equivalence classes in this partial commutation monoid.
Well, see, the stable set enumerator is well defined. Every monomial is well defined, even in this partially commutative algebra, because they're stable.
That's right.
They can all commute.
That's right. So it's exactly so this.
But then when you invert it, you have to be careful. Then you start having to work in this partially commutative algebra.
Well, yes. So you can still separate z of g minus x out into the constant term, which is 1, plus higher or minus higher order terms, and expand that as a geometric series.
Right. But I mean, each higher order term is well defined without any worrying about ordering.
Right.
Then when you expand the 1 over, you have to be careful about ordering.
Yes, exactly. And that's precisely.
I mean, you could always write this as a z, this thing times the sum on the left-hand side equals 1. So.
And in fact, that's the proof. You take this and you clear the denominator. You can multiply it on the left or the right, doesn't matter. And then you construct a sign reversing involution that kills off everything except the constant term. And it's a very simple involution as well. Yes.
Can you repeat the definition of this equivalence relation?
Yeah. The equivalence relation is the coarsest equivalence relation on monomials that allows these commutations but no others. So you're allowed to permute variables that are non-adjacent.
So what is this finite string of vertices? You have really finite string of vertices?
Yes.
Like that?
Yes.
This is an element of this set. Okay.
Maybe I can give you
Finite strings of x's associated with it.
Yes, it doesn't matter. I mean,
Finite string of x of I.
So I take monomials in x's somehow.
Yeah.
so
If I can bring them by commutation to the same, then it is the same type. Yeah. Okay. So monomials.
So x2, x1, x3 is equal to x2, x3, yes, x1, because x1 and x3 commute. But it's not equal to x1, x2, x3, because x1 and x2 do not commute.
And the left-hand side of the identity is for each inequivalent monomial, you take it once.
Yes. So you take one representative from every equivalence class.
So if you take your stable monomials and you look at the complement, it's a monomial ideal. So do you have any counterpart? I mean, if you look at your identity, could you generate a counterpart in the V star modulo that would connect the monomial ideal to some counterpart?
I don't know. I mean, that's using monomial ideals of non-commutative rings, which I don't understand too well. There's probably something to be done there. Yeah. Okay, so I mean, the proof is really quite simple, but I want to talk about a lot of things lightly instead of doing anything seriously. So there are also a number of other formulas. You can perturb this formula by putting in a numerator that's more general, and then you end up with a left-hand side that's more general. And there's also examples where you have the logarithm of this instead. And all of these have combinatorial interpretations and proofs. Okay. Now this is something completely different. The only point in common with the last topic is that the proof is also a sign reversing involution. And I just want to go through this quickly. It's a very pretty identity. So the framework here is a finite connected acyclic directed graph properly drawn in the plane. So imagine it right there. I'll give you some pictures later on. And every edge has associated with it a certain weight, which is a value in a commutative ring. And I'm going to be interested in paths in this graph. The weight of the path is the product of the weights on its edges. Next, you fix a sequence of vertices in order around the boundary of the infinite face, A1 up to AK, ZK down to Z1.
These are not necessarily all the vertices, just some.
Not necessarily all of them, and not necessarily distinct. Yeah.
What's the infinite?
It just means the unbounded.
The non-compact face. Yeah. And I'm going to be concerned with these generating functions. M, AI, Zj is the sum over all paths from AI to Zj, the weight of that path. So here's a sort of schematic picture of what's going on. Here's my graph, and I've got A1 up to AK here, Z1 up to Zk here, and think of all of the edges being directed upwards or something like that. So here's a path from A2 to Z1, and the weight of this path is the product of the edges that you meet when you traverse that path. And then M of A2 Z1 is the sum of the weight of such paths as the path varies over all paths with endpoints A2 to Z1. So those are the ingredients. Now, this Carlin, McGregor, Lindstrom, Gessel, Viennot formula is a generating function for the set of all k tuples of paths where pi goes from ai to zi, and otherwise they're internally vertex disjoint. So there are ways for these paths to migrate from the starting points to the ending points without touching one another in between. Where?
No, because he had them in the order.
Ah, yes. That's why I labeled them in this way. Yeah. A1 to AK and then ZK to Z1. Right. You're exactly right. And that's why planarity is important. Yeah. Okay, so here's a formula for this generating function. It's the determinant of the m's. I remember having chills the first time I saw this. I mean,
This is if you understand single paths, you understand k-tuples of paths with the constraint that they're internally vertex disjoint.
exactly. Yeah. Yeah.
What was that again? What's it called?
Go back to M.
Yeah. So what I'm summing over on the left-hand side are k-tuples of paths where path P1 goes from A1 to Z1, P2 goes from A2 to Z2, and so on. PK goes from AK to ZK. And on the inside of the graph, they have no vertices in common.
What is the M again?
What is M? Capital M.
One slide back.
I'm sorry. M is just the always, it's the generating function for paths going from AI to ZJ.
Those are single paths.
So yeah, so this is a generating function for a single path with these endpoints. And if you know,
all possible I and J, and over there you are only from I to I, J to J.
yes, that's right. But if you require these paths to be internally disjoint, then the only way it can happen is that A1 must go to Z1, A2 must go to Z2, and so on because of planarity. If you had A2 going to Z1 and A1 going anywhere else, they have to cross at a vertex, and that's forbidden.
Think of time going up and space going horizontally.
Yes. Yeah, in fact, that was Carlin McGregor's original interpretation.
What happens if inside they have to meet? If there is a bridge inside somehow they have to. So then it's 0, but why it is
yes.
0 on the right is determinant why it is 0.
Well, because
It's just one pass.
you get it from the proof, because what happens is you look at all paths which are all sets of paths which are not internally vertex disjoint. So there must be a vertex that's on at least 2 such paths. There's a first path that contains such a vertex. There's a first such vertex on that path. There's a first next such path that passes through that vertex, and then you do a little sign reversing involution, and it cancels everything.
But why that contains only one?
So if you have a
Yes.
So you have 2 rows.
Patients, and then you find a clever way of in a reversible way. Yeah.
But you could have taken all the edges to be independent variables, and you are universal, and then you can evaluate at your commutative ring. Right?
Yes, exactly. Exactly. So you might as well put a different indeterminate on every edge.
You did
With-
do that.
Yes, essentially. That's Allen's multivariate philosophy. So here's an application. On this particular planar graph, I'm going to consider the edges directed from left to right and from bottom to top. And I'm going to put vertical edges get weight 1, and horizontal edges get an indeterminate weight that just indexes their altitude. So everything in the first row is x1, everything in the second row is x2, everything in the third row is x3, and so on. Now consider a path from A1 off the top of this chart. You could cut this off at some point if you want to. So a path from A1 up to A plus k infinity. So it doesn't have any more horizontal steps after this. So it's a product of infinitely many ones. That's okay. So this is going to have x2, x2, x4, x7, x7. And the generating function for all paths from A1 to this point is the complete symmetric function hk, because you just read off a weakly increasing sequence of subscripts to tell you which path to follow. So this is the analog of one of the MAZ things. So this path is encoded by the sequence 22477. Now, what if I have a bunch of internally disjoint such paths? They start at some of these vertices down here, and they go off the top of the chart at some points as well. This collection of paths is encoded by this tableau. Each row is of the type, is encoding one of these paths. So this middle row is encoding the middle path. The top row is encoding the left-hand path. 1, 1, 3, 6. And the right-hand path is the bottom row, 3, 5, 5, 8. And I've indented them in such a way that there's a compatibility condition. You see, these are weakly increasing sequences in order to encode paths in this directed graph. And the columns are strictly increasing. And that encodes non-intersecting vertex disjointness here. It's a little bit difficult to see how it works exactly, but let's take a look at this first edge of the right-hand path. That's this one here. So this column here, 1, 2, 5, corresponds to this edge, 1, 2, and then this edge, 5. Similarly, let's say this column, 3, 7, 8, corresponds to the third edge in the right-hand path, 3, 7, 8. And you see, this is a near miss. And this 7 is 1 less than that 8. And if this 8 were a 7, then these paths would fail to be internally disjoint. So it's the fact that this tableau is strictly increasing down the columns that corresponds to these paths being internally disjoint. Never mind the details about how that works exactly. There's also some detail about how to change the starting points and the ending points into the shape of this tableau, but I don't really want to get into that. The point is that the generating function for all the tableau of a given shape is a symmetric function. That's a little lemma of Bender and Knuth. It's called the skew-Shor function. And so if you apply the Carlin, McGregor, Lindstrom, Gessel-Viennot method, you get this formula for skew-Shor functions in terms of complete symmetric functions, which is a classical result of Jacobi-Trudy, a dual form actually. So this is important because the ring of symmetric functions encodes a lot of very subtle information. In particular, all of the representations of the symmetric groups are built in. Also, these are, in some sense, the generic minors, or the minors of a generic Toeplitz matrix. A Toeplitz matrix is an infinite matrix that's diagonal, that's constant on the diagonals. So there's a lot of nice algebraic combinatorics that can be subsumed in this combinatorial constructions. Okay. Well, so I don't have much time left. The next thing is the Kirchhoff's matrix tree theorem. I'll just kind of.
There is a question.
Oh yes, I'm sorry.
I wanted to ask, there's another formula for skew-Shor polynomials where you take determinants of hook shapes. So you take your shape and you cut it up into hooks about this diagonal.
Mm-hmm.
Can you sort of obtain that using Gessel-Viennot?
I don't know. I mean, there's a dual form of this one where you have elementaries instead of completes. And I think you can probably do something for what are called super-Shor functions, or where you have these things that interpolate between elementary and completes. But I don't think that's the same as hook shapes. So I'm actually the wrong person to ask about this. It may be. I don't know. The question is, it comes down to whether or not you can interpret the Shor function of a hook shape as a lattice path in some graph. And if you can do that, then you have a very good chance of producing the determinantal formula. Yeah. So it may be the case. There are a lot of very smart people who do tableau combinatorics. Okay, the matrix tree theorem, very briefly. So you've got a finite connected graph. It could have multiple edges. You might as well say it has no loops, but it doesn't matter. And just as Bill did when talking about the flow polynomial, you put an arbitrary direction on each edge. And I'm going to associate with that a signed incidence matrix. It's indexed, the rows are indexed by vertices and the columns are indexed by edges. And the VE entry is +1 if E points into V, -1 if E points out of V and 0 otherwise. Also if E points out of and into V. So if E is a loop, the corresponding entry is 0. I'll give you an example in a moment. And now, put an indeterminate on every edge of the graph. So I'm calling them Y instead of X because the X's went on the vertices. Look at the E by E diagonal matrix of these indeterminates and form this Laplacian matrix, the weighted Laplacian matrix. It's just dy d conjugate transpose. D is a real matrix, so it's just d transpose. So this is a kind of a discrete analog of the Laplacian operator.
So what was D?
D, sorry, is this matrix with these entries. So here's an example. This is a random graph with 6 vertices and 11 edges that Maple produced for me. And this is a signed incidence matrix for it. So the third edge goes from vertex 2, out of vertex 2 into vertex 4, and so on. And then you just form the weighted Laplacian matrix. It looks like this. The off-diagonal entries are negative some edge indeterminate, and the diagonal entries are the sums of all of the edge indeterminates incident with that vertex. It's a square matrix indexed by vertices. Okay, it's a singular matrix. It's easy to see that it annihilates the all ones vector. So its determinant is 0. But if you fix any vertex at all and look at the submatrix that you get by deleting row V0 and column V0, then the determinant of that submatrix is the generating function for spanning trees that you wanted to know about. Right? So it's exactly the same. If you had all of these variables equal to 1, that's kind of the classical matrix tree theorem. But this is the classical matrix tree theorem from the multivariate philosophy point of view. And the proof is all the same. The proof uses Binet-Cauchy and this lemma. This is the key lemma. Basically, it's just something about determinants of subdeterminants of the signed incidence matrix. Oh, this is a mistake. This L should be D. That's bad. So this is the signed incidence matrix, and I have a set of vertices and a set of edges that in total sums up to the total number of vertices. Okay. So if I delete these rows and keep these columns, I get a square submatrix. And the determinant of that square submatrix of the signed incidence matrix is plus or minus 1 if V, together with the edges in S, is a forest where every tree in the forest has exactly one vertex in the set R. And otherwise, the degree of that submatrix is 0. So this requires a small induction proof to do it, or something like that. And you put it together with Binet-Cauchy, and you get the matrix tree theorem. But you get more. You get the principal minors matrix tree theorem. So you can delete any set R of rows and any set R of columns from the weighted Laplacian matrix. And the determinant of that will be the sum over all spanning forests where each component in the forest must have one of the vertices, and then exactly one of the vertices in the prescribed set R. So here again, I'm just using this shorthand notation. From that, you can get this determinantal identity for spanning forests, but there's a catch. You don't get every spanning forest exactly once, you get it many times. Once for each possible way of putting root vertices on the components. So the spanning forest will occur with multiplicity equal to the product of the sizes of the components in that forest. And that's annoying. That's not what I want. I want a formula for this. And it was found a few years ago by Caracciolo, Jacobson, Soler, Sokol, Sportiello. That's this introduces some notation which is hard to define. So I just want to give you a feel for what's going on here rather than a proof. There's these psi's and thetas. These are anti-commuting indeterminates, or fermions. So that's why I call this the four-fermion forest theorem.
NJ vary over what set?
So this summation is over the set of all edges, and this indicates that the edge E has endpoints I and J.
I and J is over the vertices.
I and J are vertex indices, that's right. So what's going on here is the following. So this is just a particular ordering in which to put the differentials. And I've got two fermionic indeterminates for every vertex. Psi 1 and theta 1 for vertex 1. And they anti-commute. Also, psi I, psi j is equal to minus psi j, psi I. So in particular, psi I squared is 0. And this is called a Grassmann-Berezin integral, which makes it sound a lot scarier than it actually is. It's just an operator that you apply to a polynomial in these fermionic variables. It says you only keep the top degree part where every variable occurs exactly once. And you have to keep track of the sign because these things only commute up to sign. So it's a specific recipe for keeping track of the signs of these top degree pieces. Then everything else is just irrelevant.
Can you go back? So every vertex has two variables, psi
Yes.
and theta, and they commute. Or
They anti-commute.
and how about the psi and theta from different?
All the Greek letters anti-commute.
Everything.
Yeah. So this is the starting point. A determinant can always be expressed as a Grassmann-Berezin integral like this. And here, theta m psi is just what you would get if you think of theta as a row vector and psi as a column vector. It's just ordinary matrix product of things. So I just want to mention that so that you can compare it with what's going on in this formula. This first term here is exactly what you get for the determinant of I plus L, which was overcounting the forests. So this four fermion term here is compensating for that. It's canceling off the overcounting. Really very nice formula. Yeah? No, I'm not saying that this is comprehensible at this point. It's just pattern matching. So here's the idea, is that traditionally every vertex is got a commuting indeterminate xv associated to it. So that's a boson. But in this picture, these bosons are composite, made of two fermions. And basically you do something very akin to exponential generating functions on that integral. You interpret everything combinatorially, match things up, and you get some very pretty sign cancellations. And what's left over is exactly the set of spanning trees, each counted once. The details I'll leave for some other time. So that's really it, and I just want to leave you with one final thought because I know the last part of that was, kind of impossible to process. So here's a quotation from James Clerk Maxwell. There's a department of mind conducted an independent of consciousness where things are fermented and decocted, so when they are run off, they come clear. So just let some of those ideas settle maybe in that domain, and when you see similar patterns in the future, it might ring a bell. Okay. Supersymmetry?
Yeah, the point is that formula. Go back.
Yeah.
So this formula has integrals in quotation marks only over fermions, right? The psi and the theta. But there's a way of rewriting it where there's integration over fermionic variable, these two fermionic variables at each site, and one bosonic, that is ordinary real variable at each site, so that the formula is manifestly supersymmetric. There's an invariance group that mixes fermions with bosons.
So it's not that the boson at the vertex is composite, it's that it's got two supersymmetric partners.
Right.
Okay,
exactly.
so-
so in this version of the formula, the boson has been integrated out, and you just see only the fermion. And in this version of the formula, there's a supersymmetry, but it's hidden. There's an alternate way of writing it where you put the boson back and you have a manifestly supersymmetric formula.
So here's a question with an obvious answer. What is the supersymmetric partner of a vertex called?
I'm sorry?
What's the supersymmetric partner of a vertex?
No,
What should it be
at
called?
At each vertex,
There's
you
a
have-
bosonic degree of freedom, which
you
is the
have a
vertex.
bosonic degree of freedom and two fermionic degrees.
Right, the bosonic degree of freedom is the vertex, and the two supersymmetric partners should be vertinos.
You actually know the language.
So that's, yeah.
So could you put back your identity on the trees, not on the forest, on these square free monomials that you have from the trees?
This one?
Right, right. So, do you have a dual formulation on the vertices? Because the dual formulation of the vertices, the monomials, should be the monomials whose exponents are the parking functions of the graph.
I think
There
that
might be some kind of determinantal identity on the sum of the monomials.
you can get that, I
associated
think,
with
by,
the parking functions.
you should get that, oh, for parking functions, I don't know, but you
So
can,
take the monomials, so you have vertices, so there are not enough vertices in order to generate something like that with square free monomials, of course.
Mhm.
So you need higher power. So what powers? The only natural things that correspond to the number of trees that you have is the parking functions. The monomials must be the parking functions. So you sum all the monomials with the parking function, now you have the counterpart of this polynomial. And now you need to find the determinantal identity as it is dual to this determinantal identity.
right, okay, so the set of parking functions is equinumerous with the set of spanning trees, but there's no natural bijection between the two sets.
Well, there are.
Well, they're not natural, they depend on a fixed total order of the vertex set.
Yeah, I need to order the
Yeah.
vertices. It's
You
not
or-
order independent. I need to have some structure
Yes,
on the
yes,
on
that's
some
right.
structure on the edges in order to get the bijection.
Right, right. So as far as I know, nobody knows how to translate this in a nice way into parking functions. That's a question that's well worth looking at. Yeah.
If you go back to the formulas with the integration,
Whoops.
Yes, that one and the previous one. If the order of the matrix, that is the number of vertices, is n, could the exponentiation be replaced by power to the n divided by n factorial?
Oh, it's actually even easier than that. When you exponentiate something like this, you just truncate it after the
That's what he said.
1 degree.
That's
Oh yeah, I
But
see.
you
Yeah,
don't
that's
take
right.
one term, you take all the terms up to a certain point, and then
No.
past a certain point you get
No,
zero.
No.
because
Anything squared is 0.
no, because all the terms that survive the integration have to be of degree 2n, and the gadget that's being exponentiated is degree 2.
Well, some of them are degree 2 and some of them are degree 4.
Some of them are degree 2 and some are 4.
Yeah.
Okay, but then in the previous formula, where you exponentiate theta m phi,
Which,
yeah, that one.
okay.
Could you replace the exponentiation by power to the n divided by n factorial?
I guess so, that's
Yes,
where you,
sure.
that's where you get, that's where the identity comes from, right?
Okay, okay.
Yeah.
But in the second one, it appears that you need all n terms, or something like, or you need more than one terms of the exponentiation power series because you don't have a homogeneous
Exactly.
argument to the sum terms are of degree 2 and the things that are subtracted of degree 4. Okay, good.
So if the number of vertices is odd, the second term does not come in at all?
Why?
Yeah, this term is just the sum over all edges. You've got one term for every edge, and then you just take I and j are the vertices at the end of that edge. So it doesn't matter if the total number of vertices is odd or not.
I don't know. I don't see.
The question about the definition of weighted Laplacian. In the traditional Laplacian, without weight, okay, that one you will have to delete one row, and then and you take the dn times d conjugate.
Yes.
Now, do you need to delete one row in the weighted portion?
So
I don't know. You try to understand.
so this matrix here is still singular.
Oh.
Yeah. If you sum every row, you get 0. So you still have to delete a row and column to get a non-zero determinant.
Okay.
I have a question actually, this is more for Alan. So this quartic term effectively acts as a counter term.
Say this again?
This quartic term effectively is a counter term which is introduced to compensate for overcounting.
Counter term not in
Like
the
as in
quantum field theory sense, but just in the combinatorial sense.
Yeah, so it's
Yeah, the proof.
The only other example of something like that with a combinatorial application is a paper by Paul Zinjustin counting some knots, and he needs some counter term like that to compensate for some relations.
No, but that's
Is
completely
there other
different. That's
examples?
in a quantum field theoretic sense.
This is just.
There's no
I'm trying to remember. Would you remember our proof?
traditional term in the explanation.
I mean, what does it come down to? If
No, but I mean, in Paul Zinjustin's paper, he's doing something like finite renormalization in the sense of quantum field theory. Here, I mean, there is no such thing. It's just kind of
I don't think we're
combinatorics.
talking about the same paper.
I'm pretty sure we
It's a counting problem. He's counting some. I don't remember exactly the class of.
Yeah,
he
alternating
uses
knots,
he
right?
calls a flip, and
Up
he
to, yes.
compensates this overcounting using an additional term, which I guess is explicit. It's not like in quantum field theory where the recursive definition. But, it's the same idea. I mean, the same philosophy. And I was wondering if there is other combinatorial problems where this is used.
Can I try to remember how the proof goes? Roughly speaking, this is actually a special case of a more general formula where each tree in the forest can either be rooted at one vertex or can be rooted on one edge.
Here, this theta I psi is rooting the vertex.
Right.
Rooting
So the
thing
vertex.
at-
So in that term,
That's
you
rooting
put,
at a vertex.
you put a ti.
And this is
for
rooting
the
it at an
vertex
edge.
Rooting,
Right.
and you put a ue for the edge rooting. Every forest gets weighted at either one vertex or at one edge. Okay. If you specialize to the case where the t's and u's are all equal, then what do you get? Every forest can be weighted either on, each tree, let's say you have a tree with n vertices, it can either be rooted at one of the n vertices, and you get n, or it can be rooted at one of the n minus 1 edges, and you get minus n minus 1, and n minus n minus 1 is 1. So the point is, the general formula includes, as a special case, the matrix tree theorem that he discussed earlier that has vertex rooting, and then you get a factor of n for each n vertex tree. The one that it's true, but it wasn't really what we wanted.
Right. You put a
but then
t
you get
here.
this n minus 1 is 1, gives you forests with flat weight. And I should say, we didn't really invent this. There was really a paper in the proceedings of the AMS by two physicists 20 some odd years ago that really had this, but in an incomprehensible way. And we kind of reinterpreted it.
Who were the two physicists?
I don't remember their names, but it's cited in our paper.
They were Chinese names.
There were Chinese names, but I think they were American. But anyway, yeah, they had it in a form where they wrote down specific formulas for the number of K component forests. And so what we realized is two things. If you collect all this stuff in a generating function, it becomes simpler. And once you do that, the thing can be reinterpreted as a Berezin-Grassmann integral.
Yeah, and it has supersymmetry.
And, right, and finally it has a hidden supersymmetry. Now whether this formula is actually useful for anything, we don't know.
If it's useful for anything, I think I have a problem for which this is exactly what I need. That is, this is exactly what I need. Whether this is exactly what I need, I don't know.
Well, I mean, the problem is that in some sense it's useless because nobody knows how to compute the right answer.
But you should be able to calculate formally and, construct some gadget built out of these things, use this in the same formula, and then hopefully calculate some cancellation to get...
The right-hand side looks nicely, but somehow if you really want to compute, so what you are looking for the highest term in the expansion, so you essentially write the expansion, so it's somehow it's not that useful as it looks like, because it's somehow not that simple as it looks like. So
right. Well, Grassmann-Berezin integration is actually a way of making beautiful-looking formulas that when you actually write out what they mean, they're complicated.
Yeah.
If you reintroduce the bosonic field, then you would have a vertex which is theta I, psi I, and phi I.
Yes, exactly.
So what happens if you integrate the fermions? What kind of integral do you get on the boson?
Can't.
Can you do it? It's at most quadratic in the fermions.
I guess you could actually.
We didn't try. Let's try it.
you will get some determinant. You will get some.
You'll get some determinant. Right.
Maybe that's
You
the
will have
determinant that
integrals
you were
from
asking
the
about.
with respect to bosonic.
But you have a bona fide integral.
Yeah.
No, wait a minute.
Generating function.
No. The problem is that
No,
it's
you
quartic.
can't-
It's quartic in the fermion. So at least physicists.
No, but
know
this
how to-
quartic appeared because you integrated out the...
No, it's quadratic, but with a constraint is the problem. And you can solve the constraint for the bosonic variable in terms of the fermionic variable, but not the other way around as far as I know.
What constraint?
Oh,
Maybe
that's
this is
the
getting too technical.
supersymmetric thing.
Yeah, maybe we should discuss it over lunch.
I have one more question. You mentioned the quantum version of the McMahon master theorem. Is there a quantum version of Lagrange, multivariate Lagrange, because it generalizes?
Yes, that's a good question. As far as I know, not yet. But there's no reason to think there shouldn't be one. Yeah.